at Yelp. What we do in the data streams team is pretty much the team that is responsible for the entire streaming infrastructure. There are actually a few teams within data streams. We have a team that is responsible for the overall Kafka deployment, Kafka discovery infrastructure, and then schematization, schema registry, kind of core libraries to produce and consume from Kafka. Then we have a team that is responsible for Flink, Flink deployment and some Flink applications, and a team that is responsible for building connectors and also running connectors. In the presentation today, I'm going to talk about how we introduced Beam in our existing Flink infrastructure. We have been running Flink for about 2 years and a half now. And the goal is for us to be able to run Python code in stream processing applications. Yelp is a Python shop, so most of our business logic and applications are implemented in Python. I'll start the presentation with a little bit of an overview on the Yelp's data pipeline, so that gives a little bit of context around the infrastructure we are running, and then I'll kind of dive a little bit more into how we are integrating Beam. So Yelp's mission, if you have used Yelp, is connecting people with great local businesses. We do this by pretty much creating interaction between users and businesses, whether it's like adding yourself to a wait list, reserving a table at a restaurant, or like searching for the best coffee shop in the area. To do that, we actually process an enormous amount of data, and obviously the faster we create these connections and the more accurate these connections are, the more value is derived for both users and businesses that are our customers. So over the past few years, we have been shifting from, say probably 5-6 years, we have been shifting from a batch-oriented world that was based on Adobe, and this is an open source library called MRJob. It's a Python library to write map-reduced jobs. It's something that Yelp open sourced years ago, where we had latency of hours or days, and over the past few years, we've been shifting to a more real-time world, where the latency is of seconds or minutes, and we run pretty like newer technologies, newer tools. Today, streaming is actually powering a lot of Yelp's features. I would say probably like the core of the business is powered by streaming. So we go from notifications to user search. Our indexing pipeline is actually in the process of migrating from a legacy infrastructure to an infrastructure that is fully based on streaming. We have some transactions flows powered by the streaming infrastructure. For user personalization, we do extract some features in real time, and also features that we extract in batch. They are actually pumped into our data pipeline, so they can reuse the connector ecosystem to store the same data in different data stores. So for example, if you're training a model, we would use our data lake to do offline training and store historical data, and Cassandra, for example, for online predictions. And we have ads and also product development. We build our guardrail metrics of the streaming infrastructure. So the overall, we use guardrail metrics to evaluate experiments result, and that's also powered by streaming. So if I look at how we have slowly introduced new tools at Yelp, this is kind of what the timeline looks like. I think interestingly, the data volume within the streaming infrastructure has been increasing every time we've introduced a new tool. So for example, when we built the actual data pipeline, we introduced Flink, that opened up to so many new use cases that we started building many more applications. That means that actually the data volume started growing by much more than it was before. Obviously, that comes with some complexities because it's growing the scale, which means if you were running some tools before that were fine and they were able to just support the use cases, now with the increasing scale, it's possible you actually need to go back and reevaluate tools that you were running because they can't scale anymore. And that's what happened for us. One of the most important pieces of our infrastructure is the data pipeline, which is this. It's basically how we brought kind of order and structure in our streaming infrastructure. We went from like just producing to Kafka topics to creating schemas, having a schema registry, and standardizing on a wire protocol and how we actually represent messages in Kafka. And then we pretty much created this contract between data producer and data consumers, where producers basically don't directly interact with Kafka anymore. They don't really need to know about topics, but they register a schema, produce data to a schema, and that's abstracting away the entire kind of Kafka lower level infrastructure details. And say for consumers, they basically want to consume from a schema and automatically deserialize the data and have kind of the proper structure that they would expect to have. So the first use case for our data pipeline was to get data from MySQL to Redshift. We used to do that in batch. We couldn't scale anymore. Started doing that in streaming. The first thing that we built was a MySQL source connector, and then we built a Redshift sync connector to get it into Redshift. We need to transform the data. To do that, this was probably 2016. We introduced a framework called Paastorm. That was really for us the answer to the lack of a good open source Python framework. And what Paastorm is really this thin wrapper around Kafka producer and consumer. It can encapsulate some best practices. There is quite a bit of boilerplate code that you need to have to implement a proper Kafka consumer producer. This was just abstracting all of that away, and it was also integrating with the serialization and the serialization and the schema registry we have. If you look at the interface, this is pretty much just a flat map. It's a very, very simple interface. It's this base class called Spalt. Users extend the class, implement that method, and they just have a stream processing application that can run and consume from Kafka and produce back to Kafka. Over about 3 years, we got over 150 production applications. That's probably mostly because of the simplicity in this API, and also was the only available alternative. This is what a Paastorm application looks like. Typically, this is an example of a Spalt that is filtering out any review that has a rating below 4 stars. Here you see basically the method. It's pretty straightforward. It's a flat map. With a flat map, you can actually implement anything. You can implement filters, transformations. If you're brave, you can start doing aggregation locally and then do more complex stuff. But obviously, that gets much harder. And then to run, we have basically this runner called Paastorm, and that will run this, which means all of this runs in a single Python process, just a consumer, it's just consuming from Kafka, and then produce all the results back there. Obviously, over time, like if you remember the graph I was showing the data growth, just a Kafka consumer producer wasn't able to scale anymore. We were scaling Kafka infrastructure, having multiple clusters. Something like that can't really consume from multiple clusters at the same time. When consuming from thousands of topics, then you start having a lot of stability issues. So we started looking for more powerful tools, and the thing that we found was Flink. What Flink really did for us was unlocking data processing or real-time data processing at scale. Introduced features that didn't really exist in Paastorm, things like stateful processing, event time processing, and then the overall API much more powerful than what we had. Developers can program against a data stream. This is actually a nice abstraction compared to like running a Kafka consumer. So we could do things like consume, like spin up consumers across like 5-6 different Kafka cluster union of them all together and just expose that entire stream as a data stream to developers that wanted to build Flink applications. Over 2 years and a half, we actually built an entire ecosystem around Flink. So the entire connectors, what we call connector ecosystem, is built on Flink. We used to have our Redshift connector was built on Paastorm. That was just not really working when we started increasing scale. It's now implemented in Flink. Cassandra source and sync connectors, Elasticsearch. We have this, our Flink SQL wrapper that allows users to build kind of more complex stream processing application they cannot build with Paastorm. They can use Stream SQL. They just have a config file with a SQL query, and we just run that for them. And then we have these other components, things like this joinery. It's a component that just runs unwindowed stream joins over streams that represent table change logs. Or like sessionize something, create sessions from event logs. If you notice here, what we are creating is basically this modular infrastructure where these components are all independent and they consume from Kafka and produce back to Kafka, and then you can kind of plug them together to build a more complex pipeline. Obviously, this came at a cost. The entire data pipeline stack was implemented in Python, so we had to re-implement the same stack in Java. We actually used Scala. We could do that because we felt it was probably like mature enough. That was okay for us to have 2 versions of the library, actually 2 implementations in 2 different languages of the library, and that's what we basically continue to maintain moving forward. So any change that happens in Python needs to also happen in Scala, and vice versa. So getting all of this together, the Yelp's data pipeline stack looks like this. We have different sources from event logging, from web services to data stores where we stream table change logs. Then we have also Spark. I was mentioning before this. We get, for some Spark jobs, we get the output into our data pipeline. Then we have a bunch of different destinations. Those are our data sinks. The thing that you see here at the bottom is schematize our schema registry, sort of a kind of the brain that controls this entire system. And then the central part is basically our data transformation stage, where we, kind of before Beam, alternatives were some Flink generalizable, reusable applications, or Paastorm. And then some users will just develop a native Flink, native Flink app. So you see that here, probably in this central part, there are some limitations, and this is kind of what we are trying to solve with Beam. The first problems are with the Paastorm. It's tightly coupled with Kafka, meaning, for example, if we need to scale, we need to add more Kafka partitions. In some cases, we need global ordering, so we have only one partition. Even if the consumer application doesn't need that ordering, you can't add a new partition, so you can't actually scale. You can consume from multiple Kafka clusters at the same time. You saw the interface before, it's very primitive. Like you actually can't do anything more than a flat map. There's no stateful support. And in the end, sure, you can implement all of these features, but the cost is actually huge. Really expensive, really hard to get right. On the other side, we have a Flink that can actually solve the vast majority of use cases that we have, but the first problem for us, all of our product developers, they are used to use Python, and they don't have much expertise around Java. So there's a higher barrier of entry. Some developers probably know how to write Java applications, but still, all of the services they maintain are in Python, so they probably don't want to maintain a service that is on a completely different stack. And then there is the problem of all the business code that exists. We have hundreds of libraries, we're looking millions of lines of code that is implemented in Python. No way we are going to implement it in Java. The alternative is Flink SQL. It works really well for simple transformations. If you want to do some custom transformation, you still need to write your own UDF, and you need to write your own UDF in Java. So we are kind of back at square one. So we started looking for a new shiny tool, and that's where we found Beam. So in the next couple of slides, I'll give just a very brief introduction about Beam. I'll keep this short. So what is Beam? Goal is having a unified programming model for both batch and streaming. From a structured point of view, if you use Flink, it's actually very similar. You have a driver program that is the program that defines your pipeline, and then you run the program. Things that you get in Beam is the SDK can be available in different programming languages. So there are Java, Python, Go implementations. I believe there is also a Scala one. And then, differently from Flink, Beam doesn't come with a distributed execution environment. So you need to rely on an external framework to actually run your pipelines. And there are different runners. The one that we care about here is Flink for our use case, but there are runners for Sansa, Spark, Dataflow, and more. So looking at what is a pipeline, it's made up of P collections and P transform. P collection are distributed datasets, can be bounded or unbounded. This is kind of what gives you the unification between batch and streaming. If it's bounded, you have potentially you have a batch pipeline that you're running. If you have an unbounded data, a P collection, like a Kafka topic, now you have a streaming pipeline. P transform is pretty much a transformation step. Takes one or more P collections in input and gives you, I guess, 0 or more P collections in output. By design, all the elements in a P collection have a timestamp. Typically, if you have a bounded P collection, probably like the timestamp is the same across all the elements. But the timestamp is extremely important for streaming pipelines because that's what determines the window. So, and actually the watermark. So if you're doing aggregation based on the watermark, that's when you decide whether you have enough data from the input to consider the result of the window correct and pretty much complete the processing and emit a result. On the Python side, probably Python SDK is lagging a little bit behind compared to the Java one. But if I compare this with Paastorm, obviously I get all the things that are missing from there. So all the high-level API, get group by to perform joins, filter map, flat map. Pardo is this parallel processing function. It's used to implement map, flat map filters. There is support for Windows triggers. You can have Windows on event time, a bunch of different windows, bunch of different triggers. If you are familiar with Flink, there is here also support for side inputs, tagged outputs, so you can have different outputs from a P transform. And then there is some support for state and timers. But support for state is not as mature as I wish it was. But I think there is a lot of work happening between like state support and also Windows. I think that there is no support for late data right now. And probably the only state that is supported is bag state. It's like a list state in Flink. It's missing like map state and value state. I think this will probably come soon. But yeah, in general, it's a lot of more features compared to what we have at Yelp with Paastorm. So how do you run it? You're probably seeing this diagram in a lot of presentations if you have attended talks yesterday. So I won't actually talk too much about that. But basically running it relies on this thing called portability API, at least for Flink streaming pipelines. For other runners, there are also other solutions compared to the portability, but this is kind of what will become, I believe, the standard to run Beam. So the portability API defines this like API to run pipelines. It's your pipeline, you write your driver program that gets converted into a protobuf representation of the pipeline that is consistent across all runners. That gets deployed into like a translator that's called job server. That translator will translate that protobuf representation of the pipeline into the framework-specific pipeline operators that can implement the pipeline that you had implemented in Beam. And then, because your framework may not support the programming language that you're using, so for example, Flink doesn't support Python, so what happens is that we have an operator that is launched by the executor itself that will spin up the language-specific SDK and run your own UDF there. So to actually look at how this works in a diagram, this is the Flink runner. It's a very simplified version. There is also like kind of artifact staging area, but this kind of gives the idea. You have your driver program. submit the pipeline. That's a protobuf representation of your pipeline. It's basically an expanded version of your pipeline. It goes into the Flink runner. The Flink runner will run the translation. That means that it will match the P transforms that you have in your Beam representation, in your Beam pipeline with Flink operators, and then submit that job to the Flink job manager as a job graph. Job manager will do the usual stuff. If you're familiar with Flink, it will distribute the subtasks across all the task managers. And then to run functions in the specific programming language, there is this component. It's I think it's called external executable or remote executable do-fun operator. Anyway, it's a component that will launch this SDK harness or SDK worker into a separate container and then communicate with that container via gRPC. There are 5 gRPC services. Here there are 3. Kind of most relevant are like just sends data, sends back and forth state, and then gets the logs from the Python worker back into the task manager. That's really important. If you are debugging pipeline, you are logging everything in Python side, but you can actually see all of your logs, including exceptions, in the task manager log. Really, really useful for debugging. So I guess now we know the API more or less. We know what Beam is and how it runs in Flink. So how do we, if we have an existing pipeline, what do we need to do to integrate Beam in that pipeline? For us, it means doing 2 things. Being able to consume and produce to Kafka as a first step to be able to run Beam streaming pipelines. Second step is being able to decode and encode these data pipeline messages so that from a developer programming against Beam, they still see the exact same representation of a data pipeline message that they are used to when working with Paastorm and when working with Flink. There are a few different ways of doing that. When we started, there wasn't actually a Kafka I/O for Python. It may not be actually available even today. I think there is some work going on with the expansion service. What we ended up doing for a few different reasons was to kind of attach Flink, our own Flink operators to the Beam pipeline that gets translated. Few reasons why we prefer to do that is, first of all, our data pipeline consumer and producer are actually probably fairly complicated. It's not just a Kafka consumer or a Kafka producer. There is like some Yelp specific code, for example, to discover Kafka clusters or to deserialize. There is like a bunch of different metadata that we still emit from those components. And the question was, even if we had a Beam similar component, do we actually want to implement the same features there and then keep maintaining also that additional component? There was also a lot of over 2.5 years of experience in Flink consumer and producer. So it's like, do we want to actually learn how to run a separate consumer producer component? So what we did was customize the translation layer. When I was talking about the job server that is translating your Beam protobuf representation of the pipeline into the runner-specific pipeline, we customized that so that we could attach a Yelp-specific component to a Beam pipeline. And potentially, what you get is basically like what you see in this diagram. We have our usual Flink data pipeline source that is sending data to the Beam central piece of the pipeline, and then the result goes into a Flink data pipeline sink. So how to do this? Here's a little bit of code. You basically need to be able to invoke your Flink-specific operator from your Beam code. On the Beam side, this is not particularly complicated. You need to extend a p-transform. You need to make sure that you are inferring the proper output type that's used for the coder that we'll see in a couple of slides. And you need to pass some parameters between Python and Java. This method right there is what allows you to send some parameters, anything that you want, to the Java side. We use JSON. You can use any protocol we want. And then there is this string here, this thing called URN. That is what's used to match on the translation side the actual custom translation that you want for that component. So on the Flink runner side, it's a little bit more complicated. If you look at this Python code, this can live anywhere. It doesn't need to live in the Beam fork. But for the translation right now, we actually had to fork Beam and change the Flink streaming portable pipeline translator, which is the module that controls the translations, and add our own custom translations to this translator map. The result of this, again, is basically this chunk of Flink pipeline. For us, it's not just a Kafka consumer. It's a Kafka consumer. It's actually a bunch of Kafka consumers union together, plus a map, plus something else, and then that goes to the Beam side. The important thing is that for both output and input, we in the source side, the output will be a data stream of type windowed value of an array of bytes. In the input, same thing. The input will be a data stream of windowed value with an array of bytes. So here comes the coder side. So now we have basically these two components that can send byte arrays pretty much between Java and Python. But now we need to give a proper representation to these byte arrays. The way we do that, within our data pipeline, we have this standard representation of every single message that goes through Kafka. And this is given by this message. It's a class, Python class, Scala class. The same class gets serialized and produced to Kafka. And there are a few different attributes that are standard. So we have timestamp, UID, message type, some others. These are standard. The type is standard, and users can assign their own values, but they can change the type. And then there is a user-specific payload. It can be any Avro schema with any custom type. This is what gets serialized and produced to Kafka. On the consumer side, we consume those bytes, but then we have reached the data structure with the Kafka position of the message. So we have the cluster where the message is coming from, topic, partition, offset. So the data structure that developers have available when they are building when they are transforming messages, actually the data structure you see right there. So to get there, we need to have to implement a Beam coder. Also, implementing a Beam coder is not particularly complicated. There is this coder class. You need to extend the coder class, and you have these two methods, encode and decode. These are the things that you need to implement. For us, we get like from the source, we get this array of bytes. So we take the bytes, you see the decode function, and we take the bytes and we return a message. On the encode function, instead, we get a message and we want to serialize the message and return bytes. You need to make sure that the decoder is registered, and you can register the decoder for a class. The very important thing is to make sure that all the P transforms that are using that class, they use the proper annotation, so that this will allow Beam to understand that the output type of your P transform is a message, and will allow Beam to reuse the coder that you have registered previously. All right, so how do we implement this? All of these things. We have the Python-specific integration lives in a completely separate package. Doesn't need like coder, this custom source and the sync. They don't need to live inside the Beam fork. They're separate in a separate library. We have the custom translation comes with a downside, which is that you can't use the direct runner anymore because that translation doesn't exist in direct runner. So what you need to do, you pretty much need, if you want to try to run those pipelines, you need to run them in using the actual runner that you'll be using. To allow developers to use Beam, we basically kind of scripted out all of the stuff that was spinning up a local Flink cluster, running the job server, submitting the job, so that they can more easily develop and then test their application. one difference compared to what I was explaining before in the runner is that we run the SDK worker directly on the host, and we invoke it directly. We invoke the SDK Python worker directly rather than using the Docker container. That makes it much easier for us to deploy on Kubernetes or even to debug it locally. Honestly, these two customization, the custom translation, and running the SDK worker on the host is something that we took from Lyft. They had implemented a similar solution back in February. The code is open source on their GitHub fork, so that's kind of what we used as reference. And then we customize kind of the things that we needed to change. We actually also have acceptance test for Beam. And we reuse the same framework that we use for Flink. All of our Flink applications have, we write acceptance tests for them. This framework is basically, there's this Yelp compose thing, it's just a wrapper around Docker Compose. This is responsible for launching all the infrastructure that we need, we will normally use to run a stream processing application. This is schema registry, that then called schematizer. This Kafka, and then in the same container we launch Flink Job Manager, 2 task managers, and in the Beam case also the SDK worker. And then so the only kind of difference between acceptance test in Flink and acceptance test in Beam is that we're running the SDK worker in the Flink container, and an additional container is the job server. The test case will launch the Beam job, produce some data into Kafka, and then if this job is producing back to Kafka, is also consuming from Kafka, running some assertion, and then this test will either succeed or fail, and kind of we tear down not everything, just the job, and then we have logic that makes sure that we use a new Kafka topic, a new schema, so that we don't encounter issues with like test pollution. So I come from a background in Flink, working with Flink for a couple of years, and I found like there are some very practical differences between running Flink and Beam. For me, something that took some time to adjust was having no access to the time characteristic. That's something that, if you're familiar with Flink, is pretty common. Every time you implement a Flink app, you need to specify what's your time characteristic, processing time, event time, ingestion time. Probably in Beam this is not as relevant because everything is in event time. There's also, I find it a little bit harder to create processing time windows. I feel it's not as straightforward as in Flink. So if you're coming from a Flink background, there are some differences that you need to take into account. Trigger composition is actually great. It's really powerful. But can be complicated to get right. This is actually an example of some differences. So the code at the top is how you do a tumbling processing time window in Flink. So you have your data stream, key by, create the window, and just run some process on the window of data. In Beam is slightly different. The map is what creates a key collection. Then you apply your window. You need to use a global window because all the other windows they are working on event time. And then you can't just run a Pardo on top of that. You need to have a group by because otherwise the Pardo will run on the non-window data. So the group by is what actually create the aggregation, and then you run the window on top of it. So a little bit more verbose. So how do we run Beam? In production, we run on Kubernetes. We have one Flink cluster for each Beam service, and we have one Docker image, one base Docker image, so all the dependencies that we need, and then the service will kind of customize the Docker image adding the Python-specific dependency of that service. As I mentioned before, the SDK worker currently is running on the same task manager container, so we don't use Docker in Docker, and we don't use a separate container for that. Our Flink operator looks like this. It's actually very simple. we launch task managers as replica set, and we have job manager also as a replica set, and we have a job that is the supervisor thing. This is a Yelp custom component. It's kind of the most interesting part here. What it does, it's a long-running Python process, controls and manages Flink jobs. The reason why we have this component is that initially we were running on EMR. Actually, we still run Flink on EMR. So we needed some component that was in charge of managing and restarting Flink jobs when they were crashing, making sure that checkpoint paths were properly stored, and was able to recover from checkpoints. So kind of does a lot of automation for the user so that we actually don't need to do all these operations manually. Takes also some monitoring and alerting if jobs are failing and not restarting. So internally, this kind of a diagram of the Flink Supervisor. So in our architecture, we have service-specific configs, and our supervisor will launch a new Flink job within the same cluster for each service config that we have there. Typically, Beam jobs have only one config, which means in the cluster there will be only one job running, but there can be more than one config, and within the same cluster we run more than one job. This watcher, once there is a new config, or there is a change in the config, the watcher will trigger a job start. That goes into this Beam Flink client. The Beam Flink client will retrieve the checkpoint path from our state metadata manager that stores the path in DynamoDB. We will get that path, launch a Beam job server, submit the job through the Beam job server by running the Python driver program. That, as usual, goes to the Flink side. Once we detect that the Beam job is now running on Flink, we tear down the Beam job server. It's not required anymore, and we start doing all of the monitoring through the Flink REST API directly. That includes every time there's a checkpoint, we fetch the checkpoint path, we store the checkpoint path into our state metadata manager, and then if the job is failing, we have a sensu handler that will just do the alerting. There are a few improvements that I think they'll probably be released in 2.16. One is, I think some of them were actually discussed yesterday. The first one is basically writing this translation in a jar and then being able to join the jar. This is interesting for the Flink side, because that means we won't be able to, we won't need to run the job server in production anymore. We could build the jar artifact at build time, just compile the jar, and then launch the job as a normal Flink job. That definitely simplifies part of the architecture that I showed in the previous slide. There is the second ticket, is Beam 7980, which is about running creating an external worker pool. The idea there is that you basically have this separate container that will talk with the operator that executes the SDK-specific code, and will launch workers on demand. That kind of improves probably performance, because on the Python side we can run workers as separate Python processes, but also make it better to define resources for the specific container. So you don't need to define resources for the task manager and the Python code into the same container. You can define whatever Kubernetes resources you want for your Python worker, and separate resources on the for the Flink task manager. And then something I don't think there is a ticket yet, but we basically, it'd be nice to have those custom translation portable, so that we can we don't need to maintain a fork anymore. So if you remember the first example, this is what a Paastorm sport looked like. The question is, can we actually implement a sport using Beam? And the answer is actually in this slide, because this is the code that you need to implement a sport, that base class in Beam. It's just a do fun, and there is just a method name. The name of the method that is different. One is process, the other one will be process message. The kind of implementation just allows user to start using a sport that is actually a do fun. And then the runner that you were seeing in the previous slide, the Paastorm runner, is actually a Beam pipeline that looks like this. We do a key by the Kafka partition to maintain the same semantic, and then it just applies a Pardo and gets the output into the pipeline sync. What that gives us the ability to run all of our stream processing on one engine, the Flink. We actually prototyped migrating Paastorm applications on Beam. I think for most of the simple applications that will work pretty much fine. So probably we'll be able to pretty easily migrate over 80 or 90% of our Paastorm applications. So we'll get all of those applications now running on Beam. And obviously, we want to encourage developers that are writing new applications to use the Beam native API. It's just much more powerful. There is no point for us to keep writing Paastorm apps. What this is giving us is mostly feature parity between what we can do in Flink and what we can do in Flink using Java or Scala, and what we can do in Beam using Python. So there's probably still, there's still some gap there, but I kind of think with time it'll just get closer and closer. The first use case for our Beam application is our indexing pipeline. This is like at the beginning of the presentation I was mentioning, we are migrating this from a legacy infrastructure to a more modern one. It's based on streaming. The reason why Beam is important there is that we have a ton of Python business logic for this indexing pipeline. So with Beam, we'll be able to have like complex windowing, aggregations, and reuse all of the Python code to transform the data. That's pretty much all I have. These are our engineering blogs, contacts, and if you have any question, I can take any question now.